Okay. Yeah. It looks, and then if you can try to say something.
Uh,
There you go.
Aliens are there.
Perfect. Okay. Um, hello, the two people in chat right now. Let's. Okay, so you have this. You wrote this paper with Avi Loeb. Um, you were comparing gravitons and dark energy, which could lead to the end of the universe. Um, tell me about it. I
Yeah,
like
sure.
a few things.
Yeah, sure. So firstly, thanks for the invite today. It's always very nice to meet you and talk with you and all that. Yeah. So this paper, so Avi wrote a paper sometime back where he discussed, what would happen if the graviton had mass. So I think before all that, I should like clarify what is the graviton and what is this stuff you're talking about,
Yeah,
right?
like what's a
So
graviton? Like what's a Compton wavelength? Like
yeah,
what's
yeah, yeah, sure.
lambda? Um,
Yeah,
just
sure.
briefly.
All right. Yeah, sure. Absolutely. Absolutely. So, when we talk of the four forces in nature, we have, gravity, we have the electromagnetic force, we have the two nuclear forces, right? So, all of these forces, we have, this kind of an idea that all of these forces are like mediated by some particle. So, you have some particle, which is the reason why these forces exist in the way that they are. Now, for the electromagnetic force, we have the photon, which is like very famous, right? We associate the photon with light, right? Uh, and for the nuclear forces, there are different particles. You have, the W boson, Z boson, and like all of that stuff. And it's not that pretty over there. So like let's not talk of the nuclear forces. But like similar to the electromagnetic force, for gravity, we have a particle named as the graviton,
Now,
and that tells you how creative physicists are because we just named the particle which creates gravity as graviton.
now, why do you associate a? Why is there an attempt to associate a particle to each fundamental force?
Sure,
Is it
that's a very
because
good question.
like I guess gravity kind of it can moves in waves or it can,
Yeah.
and then that gets into certain quantum aspects of maybe superposition or something. Um, is
All
that
right.
am I on track there or um,
So your question is completely on track, and this is something which should definitely be discussed. So when we talk of like any kind of force, when like what we are saying when somebody says that you have two magnets which are interacting with each other or like attracting each other, right? So what is really happening is you have photons going from like one magnet to the other, and there is a continuous exchange of those photons, and that exchange in turn is related with some quantum effects which happen at the smallest of scales, and that all of that culminates into this kind of attraction that we see from our eyes. So when we see two magnets being very close to each other and then attaching with each other, what has really happened is there has been an interaction of photons going from one magnet to the other, and this interaction was the reason why those magnets eventually behave the way that they are. So uh, you know when people started to talk of this gravitational waves thing and all that, there was this question that we have electromagnetic waves. Light is a form of an electromagnetic wave. You have more stronger forms like the X rays, the gamma rays, and all that. So would it be possible that if the electromagnetic waves are consisting of photons, and photons give you the electromagnetic force, would it be like if gravity also generates these gravitational waves, would gravity also be mediated by some exchange of a fundamental particle? And that became like a very big l- like a very big debate in the 50s and 60s, long after Einstein, passed away. And some people did work on it. There was John Wheeler. John Wheeler was the PhD advisor of Richard Feynman, who is like the sweetheart of like every physics fanatic in the 20th century, right? Uh, and that guy did some work on it. You had other very big people doing work on it. Then when this scene of string theory and like loop quantum gravity and all that started to rise up, when people were very much interested in what happens with gravity at the smallest scales, then in the 70s, 80s, 90s, this thing boomed up. So you had people, string theorists, you had low quantum gravity guys, all of these people attempting to make a fundamental theory of gravity, being interested in this idea as to how uh, gravity is mediated at the smallest scales possible. And the idea was motivated by the fact that, well, if the electromagnetic force is mediated by photons, should it be possible gravity is also mediated by gravitons? Now you could, raise quite a few points on this. Like you can say that, like if you were to think of Einstein's theory of gravity, then gravity is not really, a force in the same way that the electromagnetic force is, because gravity is just the curvature of space time, right?
Okay.
Well, then, so that is where physicists make their money, because like there is this one uh this one group which is like, oh, no, 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 it's all curvature. And then there are the particle physicists. No, 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 we want to work on this stuff. We want to work with the curvature, but we also want to work with particles. And yeah, so of course there is a big debate as to how gravity actually acts on the fundamental scale, but it is certainly worth thinking if 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 gravity has a fundamental particle attached to it as well. Now, just one more thing with this.
Okay.
So photons are massless. So we say that photons do not have any mass, right?
Now,
Uh,
when you say photons are massless,
yeah.
how does like something like a solar sail work?
Ah, all right, all right. That's a very good question. So, in Einstein's theory of special relativity, there's this one very famous thing, which is E equals to mc square, right? So that tells you that mass and energy are like inherently linked with each other. But the cool part is that, people usually write the smaller version of that equation, right? The full version is like E square is equal to m square c to the fourth plus p square c square. So what does that really mean? I don't want to go into all of the equations, but
Yeah.
but what that really means is, if you have m equal to zero, right, there is still some e that you can still have. So what that means is, if there is a massless particle, if there is a massless entity, until the entity moves, until it has some kind of a momentum attached to it, like until it is something which is moving, it has energy. So when you talk of how solar cells works, of course, photons don't have mass, but they can still have energy, because they completely, they are like completely the most mobile things in the universe. I mean, they never stop.
Okay.
So the movement of photons is the reason they carry this enormous energy with them. And that's the reason why we can talk with each other, due to satellites, the optical fibers supplying the internet and all that stuff, because everything is like, mediated by photons at the very fundamental level, of course. So yeah.
Okay. Now, in this paper, you're playing around with gravitons,
Yeah.
and there it seemed like what you were doing was you were saying like, okay, if we assume that maybe there's a little bit of mass to these, and then you started to do calculations with that. Is that right? And you were comparing that to lambda, which could you explain?
Yeah,
Also,
sure.
assume that anyone watching right now, we're all retarded. So, like,
Well, same here, because like, you need to be a little retarded to actually be working in theoretical physics. So like, I'm in the same boat as you guys.
okay,
So yeah,
you sound a lot
you know,
smarter, but go on.
Okay, all right. So, that's one of the ways you actually become a physicist. You masquerade yourself as a smart guy.
Okay.
All
Okay.
right. So, yeah. So, so as you said, so in the paper, of course, so as I was telling you about the history of this graviton thing, so,
Yeah.
the graviton and the photon, at the fundamental level have one kind of similarity, that they are, some kind of, gauge bosons. Now, again, I wouldn't go into the details of whatever that is, but
Yeah.
you can just think that, fundamentally it was assumed that these two particles were of the same family, right? So if the photon is massless, then people also thought that the graviton would be massless. Now, the cool part is that latest experiments in particle physics have also placed some constraints on the mass of the graviton itself. So they have, like, placed a constraint that it has to be less than 10 to the power minus 50 G.
So
So
they're like it has like if it does have mass, then it has to be less than this amount of mass.
yeah. So
Okay.
they place this insane constraint on it. So, when I say 10 to the power minus 50, I mean a zero followed by a point
It's
followed by 50 zeros and then one.
okay.
So
It's
these guys placed this kind of a constraint on a photon.
okay.
So then the gravitational guys thought, well, if you are playing around with these numbers, then we want to get into this business as well.
We want to play
So
with the
they start,
masses too.
yeah. So then there was this advent of a certain class of theories, which is the massive gravity theories. And, there are a few people. So you have Claudia Deram, you have Andrew Trolley. These people were, like, very influential in, like, providing the first massive gravity theories. So when I talk of massive gravity, it is basically like a version of Einstein's general relativity, where the graviton cannot be massless. So you think of massive gravitons. So this theory came about, and it became sort of successful. I mean, people started to working on, uh, and, then there were, constraints on the mass of the graviton from, like, various sources as well. So that was how this mass of the graviton thing started to come out. And recently, what I said at the start of the stream, Avi wrote a paper on November 3rd, where he, gave uh, the most strong bounds on the mass of the graviton till now. So
Okay.
he
Okay.
found out the most strong theoretical bounds on the mass of the graviton till now.
Okay. So
And really, yeah,
who did that?
Avi,
Oh, Avi Loeb. Okay, Avi Loeb.
yeah,
So by the
yeah.
way, for anyone tuning in, Ohm has just published a paper with Avi Loeb, the head of the astrophysics. Well, he was the head of the astrophysics department at Harvard, um, and he's been on Joe Rogan and stuff. Um, and okay, so Avi published that paper on November the 3rd, and he's like, okay, if the graviton does have mass, then it has to be between these very like kind of finite boundaries. And
Yeah,
then you were
yeah.
like, okay, well if it has mass, then and then okay, so and before that, people kind of thought that it didn't really have any mass, much like a photon.
So, like, there have been constraints. So, like, if you remember, there was this very good thing which happened in the history of physics recently, which was the detection of gravitational waves
Yeah.
in 2017, right? So actually, some people, worked out a constraint on the mass of the gravitons from that merger of black holes, which gave us those gravitational waves.
Oh,
What
okay.
Avi found out was, he found out an even stronger bound than the one which people found from that merger of black holes. And so that's why that's a pretty significant work. I mean, and the cool part is his paper is only 3 pages long and has this huge result in it.
Yeah, those are always the cool ones.
Yeah.
Okay, so then you get in. You I guess you contacted him, and so your theory was kind of um, well. Let's start out. Let's kind of go into like what the cosmological constant is right now. I guess because you compare that
Yeah,
to
sure, sure.
there's a lot of technical details in this, but
Yeah, yeah, yeah.
um,
All right.
let's build up the other side. Yeah.
Yeah, sure. Uh, Again, so we are like speaking of this guy so much. So this very wonderful fellow named Albert Einstein, right?
Yeah.
Comes into the picture again. So if it was not enough for him to like give gravitational waves and E equals to mc square and relativity, this was the guy who also gave you the cosmological constant. So now, but actually, it's a pretty cool story, and the cosmological constant is probably Einstein's biggest blunder, and I'll
Yeah.
tell you why.
Okay.
So,
And if
so
you
the
can
reason
also
is,
kind of like explain what it is as well and stuff. And
yeah,
yeah.
sure, 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 sure. So, so what happened is, when we talk of Newtonian picture of gravity, we say that anything which has mass attracts you to it because of gravity.
Okay.
So that was Newton's picture of gravity, that, right? Because he thought that gravity was only due to the weight of the person, right? Now that is what we are taught in schools and all that, and it makes sense, right? Now what Einstein did was he showed that actually gravity does not have as much to do with the mass of the person as it has to do with the energy associated with any quantity. So as I told you, uh, things can have energy even if they are massless. So in Einstein's theory of general relativity, even a photon, which is a massless entity, even that can be affected by gravity. So these were some very cool features in like Einstein's version of gravity. And one cool feature is, uh, you know, uh, gravity could be repulsive as well. So you can have negative gravity. So under some very special circumstances. So, instead of pulling things towards each other, gravity could act in a way in which it could start to pull things away from each other. And that is quite a startling revelation because like could you think of this that like we were to like jump from from a certain height into let's say some river, hoping to like splash into it 2 seconds later,
And you
and
just
instead we just keep on going away. So like it doesn't make sense, right? And that is what Einstein thought as well. And so he had this one term in his equations, which was inducing this negative gravity. So Einstein was like, huh, well, this doesn't make sense because now you need to remember that this was the time at which people thought the universe was a static universe. So what I mean by static is that well, of course, the Earth is moving
it's
around
just
the sun.
everything
Yeah,
is always has and has been and will be.
yeah,
Yeah.
no, no, it has to do more with the galaxies.
Okay.
So, yeah, so basically, in a static universe, the galaxies never move away from each other. They don't move at all.
Okay.
So Einstein thought that okay, so we are living in a static universe. Now gravity is an attractive force. So if there is all this mass, if there is all this matter in the universe, then eventually it will have to start to contract because things will get attracted to each other. So I think what Einstein said is, I think this cosmological constant, this this constant in my equations, which is giving you negative gravity, is the reason why this attractive pull of the galaxies is being balanced out by this repulsive pull, and that is the reason why the universe is static. So he thought that this repulsive
Oh.
term in the equations, this
Okay.
repulsive term was only there to like make things static. So he did
Oh.
this in 1917. Now comes 1929, and this wonderful fellow named Edwin Hubble was, one fine night he was like seeing up the sky. Hubble's birthday was like very recent as well. He was seeing the sky, and eventually he found out that galaxies are going away from each other, that the universe is expanding. So now get this. Einstein, just based on some equations on planet Earth in his notebook, could have predicted that the universe is expanding 12 years before people actually observed it to be expanding. I think if Einstein saw that sight, he would, I mean, I think that would have been the greatest marvel in the history of theoretical physics. I mean, if you can tell that the universe is expanding while sitting in the comfort of your cabin, while sipping a cup of coffee, you're like the greatest genius ever. I mean, he still has the claim for that, but I mean, that would have been even more insane. So that's why people call this cosmological constant thing as his biggest blunder. But I still haven't told you why cosmological constant comes in with dark energy.
So
So I'll just tell you that right away.
it's so basically everyone thought the universe was static,
Yeah,
or it has to do with the galaxies, and
yeah,
but the galaxies didn't seem to be like moving closer to each other. So
yeah,
Einstein put in this constant, this thing in his equations to kind of balance that out, and so there's a repulsive
yeah,
force,
yeah.
and then Edwin Hubble ends up discovering that the galaxies are actually moving. Everything. Would it be correct to say that everything is moving away from everything else,
Yeah,
which is
exactly.
kind of hard
And
to
that
imagine in 3 dimensions? But um,
Yeah, indeed. So, so what was actually happening is this cosmological constant was telling you that there is some repulsive nature of gravity which is pushing away all of these galaxies from each other. And if Einstein could have accepted that version of reality, I'm not sure if it crossed his mind, if he thought that this was something too crazy, which would have been odd because Einstein's whole life was made because of crazy ideas. So so basically, cosmological constant tells you that the universe is expanding, and then people thought, I mean, if we have this constant, can we measure it? Can we make some predictions about it? uh, then for like the longest time, people, again, humans have this great ability to, like, assume things which they have not much idea about, right? So then people, and like, this is like true for scientists as well. I mean, you know like a bit of an aside on this. I mean, sometimes people say that, okay, listen to the science, and like listen to the scientists, and like that is a good thing. But bro, it could happen that the scientist himself can be, disputed by one of his collaborators, or like one of his colleagues in a coming paper. So you need to just think like a normal human. These people, we are also humans, and like we make mistakes. The best of us makes mistakes. So yeah, that's a good thing. I mean, you should believe the science once it is, very much tested. But and like even if it is tested, you should, at least give some kind of a leeway towards, it, there might be something happening down there which might not be evident as such, as of now, to like everyone else, but there might be something cool, which you might observe, which the others have not. So yeah, I mean, I think the real fun of science is actually in, talking about these very exciting ideas in a sensible and technical manner, right? In a
okay.
sensible and technical manner, and trying to find out if these very, distant things really have any kind of connection with them. So I mean, yeah, this was just a small aside. So basically, people started to, measure the cosmological constant in some ways. The astronomers did, and eventually, we had this age of dark energy, where in
Okay.
1999, astronomers found out that the universe was actually not only expanding, but it was accelerating. So if we have two galaxies going away from each other, it is not like, they were, let's say you have two cars, they are moving at 60 miles an hour, right, away from each other, and the roads do not have any kind of, braking system. So like if the drivers do not put brakes on them, eventually the cars will, like, not stop, right? So eventually, people thought that that even though galaxies are going away from each other, eventually, the cars will be out of fuel, and even if you are too far away from each other, the roads might be like this, that the cars may come back towards each other. So that was like the hope. But it turns out that there is something which is not only, providing fuel to the cars, but also accelerating them away from each other. And that something is what we now call as dark energy. And dark energy literally means dark energy. It is some form of energy which we cannot see. That's why it is dark, which is expanding our universe out. And the simplest expansion explanation for dark energy that we have is the cosmological constant. We say that the universe is expanding because there is this feature of Einstein's gravity, where you have repulsive nature, and that repulsive nature is acting. You have loads of alternatives of this cosmological constant uh, in the literature as well. But yeah, this is like the simplest explanation.
Okay. By the way, in 7 minutes, you'll have to switch to your Zoom.
Yeah.
Okay.
Yeah, sure.
Okay. So now you were trying to relate the gravitons to dark energy. How'd you go about doing that?
Yeah, it sounds a bit crazy, right? So, so yeah. So what I did is, so, so I was like searching up these papers. So, so it came out that there is this very interesting paper in 2003, where like some people worked on this possibility. Uh, if like if the cosmological constant could be related with the graviton, and what they did was they did some very sophisticated mathematical work, some some very interesting jugglery with Einstein's theory of gravity, and they found a particular relation between the mass of the graviton and the cosmological constant. The relation was like very interesting. So then I talked with Avi about it, and then he actually sent notes, and like he sent notes, and in those notes he showed that the relation that these guys worked out in 2003 from Einstein's theory of gravity would not have observational significance. So I mean, it wasn't testable at all, and I was like, that is damn good.
That
So
that
then
is what? That is
that is damn good because
damn. Did you say
because
damn good or
yeah, yeah, yeah.
Oh, okay.
And the reason I say that is because it is counterintuitive in, in like so many aspects, because like so so that work was like completely based on something known as a linearization of Einstein field equations. Again, it's like jargon, right?
Okay.
But the cool part is, that result kind of like came out exactly from Einstein's equations. Now, you are finding out that something which came out from Einstein's equations. Remember, Einstein's theory has been well tested. So, something which came out from Einstein's equations might not be observationally testable at all. So, it might not have, realistic features at all, even though the math allows for that. And that was something very interesting. So then my part was that then I started to like see how general this result could be. And then I found out that then I actually constructed like the the mass of the graviton and the cosmological constant relation from like three other theories. And I found out that in all of those theories, the problem that Avi pointed out in his notes persisted. And so, we ended up saying that, okay, this is something significant, and let's write a paper about it. Because, I mean, that is quite a significant thing, right? Uh,
Well,
that
well,
in any theory, in any approach of physics, where you have the graviton being related with the cosmological constant, you have fundamental issues which will prevent it from ever being realistic. And that
could
that
Could you
that is
elaborate
significant because
that? Could you
yeah,
elaborate
yeah,
on that a bit? I'm like
yeah,
I'm a bit
because
lost.
yeah,
Like,
yeah, yeah, yeah.
okay.
So see, uh, again, see, this sentence is very strong. So in any theory of physics where you have the graviton's mass being related with the cosmological constant, there are some fundamental issues. Again, people thought that the reason why the universe is expanding is because of the repulsive nature of Einstein's gravity. Okay, Einstein's gravity was the reason why people started to talk about the mass of the graviton in the first place. Now, this paper tells you that the mass of the graviton and this apparent expansion of the universe due to Einstein's, repulsive gravity in general relativity cannot be realistically related with each other, and that is quite a fascinating thing to like think about because something which just came from GR, from general relativity, and something other which is kind of like motivated by GR are not, observationally compatible with each other. And that is quite an interesting thing. So that tells you that whatever it is which is expanding the universe, uh, you know, if that has the form of a cosmological constant, uh, then 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 basically that cannot be the reason why the gravitons have mass. It could also mean that the gravitons might not be responsible at all for the expansion of the universe. I mean, someone can like take it in that way as well. And so, that could mean that that something other than gravity is expanding the universe. I mean, that just, Richard Feynman once said that a good research paper is not something which answers all the questions. It is something which answers one question and like generates 10 others. I think ours generates 20 others. So, so that's why,
So,
it's like quite interesting in that sense.
did you find that there was something related to the graviton and dark
Yeah,
energy? Okay.
yeah.
And what?
So, yeah, so what we basically found out was that there could be multiple theories which allow for the graviton to be sourced, I mean, to be given a mass by the cosmological constant. But all of those theories have the same fundamental problem. And that is quite interesting because you think that if you change the approach by which you are, taking to a problem, then the problem might be solved. But if you take five different approaches and you still get the same result, then there is something interesting happening at the very fundamental level that we do not know about.
Okay, if you could, okay, call me back, and then if you
Yeah,
can elaborate on what that fundamental problem is,
yeah, sure.
I'd be very curious
I'll
to
do
hear
that.
that. Okay,
Yeah, just a second. Yeah, yeah.
yeah.
I'll,
Sorry, people on the stream. We're kind of ghetto. I'll be right back. Over there, looking like a cheese-eating stoner. Um, well, I'm not sure how to interpret that comment. Um, People do tell me that I always look high. I am not high though. I'm just waiting for his link. Uh, I am trying to understand this, but I like there's parts of it that um, it's like does gravity. So how do gravity and the cosmological constant? I huh, maybe I can just. Okay, we're back. Can you hear me?
Yeah, I can hear you, and I hope you could hear me again.
Yes. Let me attempt to adjust this, and I hope that this works again. There you are. Okay. Okay. Someone in the chat just put "wow" in like just big characters.
What
Someone in
what
the
did they
chat
put?
they just put the word "wow" in all caps.
Ah, all right.
What did someone say? Oh, my UFO leak video is trending on Reddit.
Th- That's great.
What was it? Wait, was it the video where that guy emailed me?
Oh shit.
Yeah, yeah, that was
Is
weird.
it that one?
I don't know that was weird. Um,
I think that could be real.
yeah, that was I mean, I continued to apparently he's gonna give me more footage, so we'll see. We'll see. I
You're gonna go big, but just look over your shoulder every once in a while now.
yeah, I'm hoping I don't get like headshot or something. I think I'll be okay. I think, but like someone, yeah, I mean, you gotta do something crazy sometimes. So,
Yeah.
anyways, okay, cool. Thank you, Dr. Melinda. All right, so you were going to explain the problem that those theories were having.
Yeah.
Um, what was the problem?
Yeah, sure. All right. So, so yeah. So when we talk of quantum mechanics, when we talk of how particles interact with each other, there's this very fundamental idea in quantum mechanics that every particle is not only a particle, so it also acts like a wave as well.
Yes.
So, so with every wave, there would be something related to that wave, which is like very fundamental to it, which is its wavelength, right?
Yeah, yeah.
Now,
I was just gonna ask that question. Like, what is the wavelength of a gravitational wave?
yeah, yeah, exactly. And from that question itself, actually, uh, this whole thing, comes about. So,
Okay.
uh, you can talk of the wavelengths of gravitational waves. You can find that out using Einstein's equations. Now, what if instead of finding the wavelength of a gravitational wave, I want to find out the wavelength of a graviton, right? Now, what we did was we
How
like
do you do
we
that?
right, all right. So
well,
yeah, I
let,
mean
let me ask you real quick. What is the wavelength of gravity?
that is exactly what I'm just gonna tell
Okay,
you
sorry. Go
in like
ahead.
2 minutes.
Okay.
Yeah. So, uh, so then we started to work out the wavelength of gravitons. All right. Now, what we found out was the wavelength of gravitons was greater than you know the observational horizon of the universe in these theories. So let me put it this way. Uh, what these theories were saying is if the mass of the graviton was due to this version of dark energy, then the wavelength of a graviton was larger than the observable universe, and that is a bit stinky. If you like putting it easily, that is a bit stinky, and that is very fishy. And now I will tell you even more interesting things. Uh, I did this calculation in more number of dimensions as well. So, for the string theorist, if there is some string theorist in the audience, I did it in 11 dimensions as well. And even in 11 dimensions, the problem still persisted. I mean, the numbers changed a little, but the problem still persisted. And so, we came to this general conclusion that in any model of dark energy, where the dark energy is represented by this cosmological constant form of repulsive gravity, there could never be a relation between the mass of the graviton and this version of dark energy. And why it is so important it is because the whole standard model of cosmology is based on this version of dark energy. I mean, you can make a thousand models for dark energy, but the standard model is this only. So what it tells you is if the graviton has a mass, it is definitely not due to this. I mean, whatever is driving the expansion of the universe as of now. Secondly, if the graviton does not have a mass, I mean, then 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 we cannot really say much about the implications of gravity on the cosmological constant. And now, thirdly, and this is a bit weird, but like weird. I mean, everything we are talking of is weird, right? So the third thing is that if someone still wants to consider, okay, if the graviton has like a larger wavelength than the size of the universe, could it mean that the graviton extends beyond the observable universe? Well, I mean, that's upon you to think. So, but in this paper, we have been a little conservative at the very last, and we have said that well, for now, I mean, this is something which you can. I mean, we can say that this could be true, but we would never be able to observationally test this version of graviton ever. And so we were drawn to the conclusion that well, this version of gravitons are not probably best suited for existing.
What what number were you getting when you tried to measure it? What?
So yeah, it was greater than 10 to the power 28 meters. So put a one and put 28 zeros after that.
And how
And
much bigger is that than the observable universe? The
uh,
horizon.
well, well, okay. So in like the three first theories that I worked out, well, in one theory it is like three times bigger, and in one theory it is five times bigger, and in one theory it is six times bigger.
Do you think it's a little uncanny that those numbers seem a little close?
Yeah, but you can actually make it. I mean, well, if you go to higher number of dimensions, you can make those numbers fluctuate. But yeah, of course, we were actually surprised as well because all of these theories come from various motivations, which are not, you know, uh, very directly related with each other, and
Okay.
still, the final calculations, basically differed by only some factors. I mean, three, five, six. There's not much of a difference. However, the approaches in which the equations were derived were like very different. So yeah,
Okay. Um, I might be asking stupid questions here, but I'm trying to wrap my head around this. Um, so okay, like we have gravitational wave sensors,
yeah,
and those can measure basically I guess you could say the wavelength of let's say two black holes colliding. Does the wavelength of that ripple in space time change in frequency, or is it constant?
all right. That is a very good question, and that is like the kind of question PhD students ask to their professors in like advanced courses on general relativity, and that is like a very good technical question.
Well, we can
So
experimentally test it, I assume.
yeah, yeah. So so like whatever sensors we make, I mean, we had this LIGO, right?
Yeah.
So we have this LIGO and like whatever ground based or like space based sensors that we have for like gravitational waves, they do measure these properties, the the wavelength, frequency of these waves. And exactly, I mean, they are made to be very sensitive because it is way harder to detect a gravitational wave than it is to like detect an electromagnetic wave. I mean, electromagnetic waves, we keep on interacting with them every time of our life, right?
Yeah.
And even if it is a very strong wave, I mean, let's say it is like a gamma ray and all that, we still could measure it. If it is something which is very weak, like an infrared, electromagnetic wave, we can still measure it. However, for like measuring gravitational waves, we need to have like a very strong, very sensitive sensor because they have like a very weak input, if that would be the right word, on these sensors. Of course, this input is like very much correlated with the frequencies and the wavelengths that you are mentioning. And eventually, from the data that these sensors measure, we can infer these values for the gravitational waves as well. In fact, I will tell you one thing. So that is not in the paper. We actually removed it. Uh,
Okay.
so, uh, so actually, we had worked out like a bound uh, for the total mass of the gravitons in the universe. So we had found out that if you take one of those, if you take one of those approaches by which you get this kind of graviton and cosmological constant uh, correspondence, one of those approaches gave you the total mass of gravitons in the observable universe. And if I tell you the number, you will be completely shocked. So this approach, so like if you were to think of that theory, so that is actually the first theory, the two the 2003 theory, which was based on that linearization of Einstein equations and all that stuff.
Okay.
If you take that theory, if you then introduce this kind of cosmological constant and graviton mass relation, then the total mass of the gravitons in the observable part of the universe has to be greater than 2 into 10 to the power 87 kilograms. 2 into 10 to the power 87. So 2, and you have like 87 zeros after that,
Yes.
and it has to be greater than that. And even after all that, even after having that huge amount of mass, gravity is still not effective. Like it is still not a strong force. Like it is still the weakest force of all of them. And we were like shell shocked seeing these calculations, and eventually we were like, okay, well, we are not putting this into the paper. So, we had more insane results. I mean, uh, like 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 the cool thing with this paper was some of the results that we took out of the paper were like equally shocking as well. So I mean, this is like a toned down version of the paper.
Okay. Okay. it's so it's I'm trying to wrap my head around the idea that gravitons have mass when mass is what appears to create gravity, or that's
It is like,
it's very confusing. But so it sounds like there are sparks of the graviton potentially being a candidate for dark energy in some way.
yeah, exactly, exactly,
Okay.
exactly.
Okay. I see. But we couldn't really
So
test it well, but or something.
yeah,
It's starting to like just really give crazy numbers.
yeah. So fundamentally, if you think about it, Einstein thought that this cosmological constant was just the representation of the repulsive nature of gravity. So if that is true, then the cosmological constant should be related with the graviton, right?
So he
But here
was
we were
like
showing,
right.
yeah, no, I
Oh,
mean he
sorry.
was right in the sense that I mean, if he was right or not, that is now up for debate, because like you have so many models of dark energy besides the
Okay.
cosmological constant, and there are so many issues with the cosmological constant, not the only one which we showed.
Okay.
But what this goes to show in the grand scheme of things is, uh, if the cosmological constant is indeed a representation of the repulsive nature of gravity, even after that, the cosmological constant is not related with the graviton. So, like, now the question is there something wrong with the theories which are on the cosmological constant, or is there something wrong on the theories which are on the which are on the graviton? So, I mean, the 7-page paper that we put out, literally pulls out questions on like so many different things.
Okay. Okay. Okay.
Because,
It
see,
sound. I am a
see,
little confused, but at the same time, I get the sense that you guys are also a little confused.
yeah, because see, the thing is that, in theoretical physics today,
Yeah.
and especially in like cosmology and like particle physics, you can make loads of theories. I mean, there are loads of good theories, right? But now, somebody like eventually you want to come to a point at which you can like rule out the other theories. You can like, see that, okay, I mean, that's a good idea, but there might be a reason why it wouldn't work.
Okay.
There should be people out there who should tell that, okay, this is very nice, very good of you to like do these to like do these calculations, find these equations, very nice, very commendable. However, this might not be realistic. Physics needs to come to that point, and at least in the community that we are, in the cosmology, high energy physics, particle physics sector, there are loads of good theories, but you need to really see which of these theories are realistic and which are not. And 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 one and, and like one approach towards that is what we have done over here. And the cool part is that like this touches upon so many different things, because the cosmological constant and the graviton both are related equally to like particle physics and like cosmology as well. So this paper, is like relevant and like significant for people who are both particle physicists and like who are both just pure cosmologists. And I cannot tell you the amount of emails both me and like Avi have like got since we put out this paper. So like people have oh, it's a good thing, I said. And like meanwhile, this is an old paper of ours. We were like thinking of this approach, and like would you have any comments on that? And like, so I mean, it might not. like it is probably not gone as viral as of now as the long freeze went, for
Yeah, that
example.
one was
But
pretty crazy.
yeah, but it has a good chance that it could go something like that as well.
Yeah, I always feel like animations help to describe
Yeah,
things like this, but I
indeed,
can't draw
indeed,
like
indeed.
draw. So I'm not sure if I'm able to mention this, but you said you're going to have more research that you're doing, and more papers that you're going to publish about this. Are you able to?
Not only about this, so like me and like Avi are like working on like a range of different things. Like there
Okay,
would be an extension of this paper which discusses you know like how this kind of correspondence works when one does not takes into account that that the cosmological constant is the only theory of dark energy. So what if instead of the cosmological constant you had the alternative theories of dark energy on hand, and you wanted to again find out whether there could be a relation between the graviton mass and and dark energy? Would it work in those models, or would it not work in those models? To find that out, as the narrator in Dragon Ball Z used to say, to find that out, tune into the next episode of our papers.
okay. I guess to close here, let me there's people are asking, there's people are typing things in chat. Let me read some of them. I'm not sure if any of them are significant. But let me see what they said. Uh, Someone says quantum vacuum and flux. Okay. Some guy said he was just trying to figure out how to change his alternator. Another person asked, "Are you using AI to speed up your research and calculations?"
So, like, should I answer that?
Oh, 1 second. Yeah. I'll be back in like 30 seconds.
So, like, release back. I think, if you want an answer to that, I think, if you were to like just blindly use AI for like doing some actual real hard calculations, then you would go to the ditch. But I mean, if you like, for example, if you have an equation and you want to plot it out, and you do not want to like write the long codes for it, you can use AI to like write your codes for that, and plot your equations out. So like in that sense, you can certainly use AI for like plotting stuff, for like data analysis. But like if you were to just think that okay, I'm gonna write this like very you know high level research paper using only AI prompts, I mean that is not gonna work. You still have to like use your brain, you have to use your imagination, and eventually in like the data analysis or like some kind of a menial task, AI might help you. But like you need ideas from this place to like
Yeah.
do some good stuff in life.
Okay. I mean, it seems like a lot of things in this field require some imagination.
Yeah.
The guy responded. He said, "Thank you." Um, Someone says release zero point aether patents. What? I don't know what that is. Okay. Well, I guess thanks a lot for sharing your paper and explaining it. I'm gonna link it in the description, um, and we'll see if it catches on around YouTube again. I mean, it went pretty. That long freeze paper went pretty hard. Uh,
It went very very hard, and like you were the first guy.
yeah. So we'll see. All right. Well, thanks. I'll talk to you later, and yeah.
Yeah, and like thank you once again for like having me in, and like it, as I said at the start of the stream, it's like always very fun to like talk with you and like just like ramble about stuff.
I try to understand as much as I can, but I haven't. Yeah, I wish I understood more, but I get a lot of it. Um, all right, yeah, I'm probably gonna make a live stream. I think about BioSETI pretty soon. Although I've been
Yeah,
saying that for
that,
6 years.
you should. I mean, at this point of time, I think this is what YouTube is beckoning finally towards you.
Yes, yes, aliens, more aliens.
Yes,
Okay,
UAPs now.
yes. All I'm doing is posting UAP stuff. Um,
That is pretty fashionable now.
yeah, yeah. I mean, well, it's more mainstream because of the congressional reports and stuff, so I feel more
Yeah,
comfortable talking about it.
yeah.
Um,
I mean, it's like interesting as heck. I mean, if it were up to me, I would, equally devote my time to like aliens research and like, do this kind of research
well,
as
I
well.
mean, you're already working with Avi. You just, um, I kind of wonder how his Galileo project's going, but yeah. Um, all right, well, yeah, I'll talk to you later. We'll stay in touch, and I'm gonna go find another alien video.
Sure.
Okay,
Thanks, man, and like have a good time.
see ya. Bye.
Bye.